So, very good morning to all of you. All of you can hear me. So, my name is Rahul Jaswal. I welcome you all to the iitiansgateclasses classes. In this session, we are going to cover some of the basic concept of fluid mechanics. That is for the demo class, and after that, we will be starting our session of fluid mechanics. So, first of all, how this session will go, I'm just giving you the overall view of that. First, we will try to look at the syllabus part, the weightage part, how to prepare for this particular subject for the GATE exam, and then, my dear friend, we have to go for some of the basic concept like a viscosity, right? That is one of the primarily a fluid properties, right? And based on the viscosity, what are all the consequences we have? That is what we're gonna look into that. Are you getting my point or not? I'm audible to all of you. So let me just share my screen. Okay, guys. So here, so first of all, we would like to we would like to discuss about the basic. What is the syllabus part? You know, so as you can see, the fluid mechanics syllabus for the aerospace. Now, how many of you from mechanical here? Any one of you from the mechanical or all from the aerospace? Okay, so can you just mention your college name also in short? Just all of you just mention your college name. Okay. School of Aeronautics. Okay. So here, Manipal. Okay. Still people are joining. So just note down, guys, the first slide of today's session. That is the fluid mechanics syllabus for aerospace. We will discuss the syllabus for mechanical also. So if you consider your section, you will be having section 1, section 2, section 3, and section 4. But in the section 4, you will have one topic called aerodynamics. One major subject is aerodynamics. The fluid mechanics, it is a part of the aerodynamics. It is not a complete aerodynamics, it is a part of the aerodynamics, right? What are all the core topics in a basic fluid mechanics? If you see the syllabus part, they have mentioned the conservation laws. Now, how many conservation laws we have? We have this mass conservation, we have the momentum conservation, and we have the energy conservations. And of course, my dear friend, here we have momentum equations. That is a well-known equation called as Navier-Stokes equations. And then we have the energy equations, both integral and differential form that we need to study. Then we have to study the dimensional analysis and dynamic similarities. So when you look at into the syllabus part, basically they have mentioned only the two topics. That is the conservation laws, and the second topic is dimensional analysis. That's it. But if you look at the question part, the question is there from the all other chapters, which is not being mentioned in this particular syllabus of aerospace. So what I have done, I have just categorized your basic fluid mechanics into 9 chapters. So please note down one by one. The chapter number 1 is a fluid properties. Chapter number 2 basically fluid statics. Chapter 3 basically what fluid kinematics. Chapter 4 is fluid dynamics. Then we have the laminar flow. Then we have the flow through pipes. Chapter 7 we are having what dimensional analysis and similarity. That is what they have mentioned in your syllabus also. The chapter 8 is basically the boundary layer theory. The chapter 9 is basically what the basics of turbulent flow. The basics of turbulent flow. So all this particular chapter we are going to cover in our 15 classes. That is under fluid mechanics, right? Out of all, you can see there is a red marking I have done. That is a star marking I have done, and this is a very important. You please mark it. If I put 5 star, you can see chapter number 8. I have kept 5 star by the red color. That is a boundary layer theory. It is one of the very important chapter. Every year you have the one question from this particular chapter, either a 1 marks or 2 marks. Again, if you see the five 5 star I have given to the chapter 7 also, that is a dimensional analysis and similarity, one of the very important chapter. If you see the recent 5 year or 6 year, every time we have one question from basically this chapter of 2 marks. Then 4 star I have given to the what fluid dynamics. 3 star I have given to what fluid kinematics. Fluid properties also I have given to 3 star. Fluid statics 2 star. Laminar flow 2 star. Flow through pipes 2 star. Very important, guys. Please make a note of it. So all of you might have studied this topic in your BTech, right? Please let me know whether you have studied or not this particular topic. Right. So what we're gonna is do in our class, we will try to do the carefully. We're gonna observe each and every concept which are involved in understanding the fundamental concept for GATE examinations. Right. GATE examination, first of all, it is very different from your BTech university examinations. Very different. Again, some of you might be aiming for UPSC after some time. Again, I'm mentioning that the GATE examination is again very different from the UPSC exam. Right. You have to remember in GATE exam, for GATE exam, what are all the things are required, to get the good rank. The first is conceptual clarity. Second thing is the numerical ability. For any topic, you should have a conceptual clarity and you should be able to solve the numerical from that topic. Generally, it is a most of the time it is very famous quote for a GATE exam is that the GATE exam is 80% or 90% is numerical oriented exam. That too, not a very straightforward numerical they are giving. They are testing the each and every fundamental of topic through particular numericals, and it is very much true. But that is what the tendency or mindset of the student also before they are appearing for the GATE exam. What they are actually thinking is that they start thinking that the GATE examination is of basically numerical ability. So I need to be robot in solving the numericals. So sometimes they start lagging in the fundamental concept or theoretical understanding, and they are very good at numerical. But remember, in GATE exam, you require the theoretical understanding also. And if you start developing the theoretical understanding from the numerical ability, that is also one of the bad thing regarding the GATE exam. And that is also one of the reason to get the no, middle rank, not the decent rank in GATE exam. I'm just telling you based on my 7 to 8 years of experience in this GATE industries. Right. With each and every chapter we will be start no I will be start sharing my experiences of the gate exam. This 9 chapter, 9 experiences I will be giving you, no need to worry. All of you have noted down? Can I move to the next topic? Now my dear friend, there is a fluid mechanics syllabus for mechanical also, as you can just note down. If you are from mechanical, aerospace need not to require anything to be noted down from this slide. You just try to observe. Observation is also very important for gate exam. In mechanical, what you are finding, they have mentioned each and everything in the syllabus itself. Unlike for the aerospace, they have not mentioned, but they are asking the question. But here they have mentioned each and everything. What they have mentioned in a section 3, fluid mechanics and thermal sciences, you will see the fluid mechanics. You will see for a fluid mechanics what you will find: fluid properties, fluid statics, the forces on a submerged bodies, the stability of the floating bodies, control volume analysis of a mass, momentum, and energy, fluid accelerations, differential equation of a continuity and momentum equations, right? Bernoulli's equations, dimensional analysis and similarity, the viscous flow of incompressible fluids, boundary layer theories, turbulent flow, flow through pipes, head losses in the pipes, bends and the fittings, and the last one is basics of compressible fluid flow. Basics of the compressible fluid flow. So the first 9 chapter which I have mentioned earlier, that I will be covering for both mechanical as well as aerospace. After that, for mechanical, I will take 4 separate classes to discuss about the concept regarding the stability of the floating bodies, you know, then concept of surface tension, capillary effect, venturi meter, orifice meter, and turbulent flow. All this thing I will discuss separately for mechanical, not in a combined class. Right? So please make a note of it. So it is always very important to know what are all the topics we need to study for the GATE exam. Just note down quickly. The basics of the compressible fluid flow I will be covering separately. That will be, in the month of maybe September, October, I will be covering the CFF flow only for mechanical. That is altogether very separate from the fluid mechanics. That is the basics of the compressible fluid flow. Although it is a part of the fluid mechanics, but I will be taking separate session for that. Done. Mechanical guys noted down. Now, the standard reference book that we need to follow for this fluid mechanics. As I mentioned, the 5 textbook. What are all the textbook which I have mentioned? First is Sinjal and Simbala. The second book I mentioned is Frank M. White. The third book which I mentioned, Som and Viswas and Chakravarti. Then K. Subramaniam. And the fifth one is R. K. Bansal. Now, most of you might be following the FM White. That is one of the very decent book for fluid mechanics and highly appreciable content regarding this particular textbook. So you can follow FM White or you can follow Sinjan and Simbala. Those who are finding difficulties in understanding the language, they can follow Sinjan and Simbala. It's a very easy. Even child can also understand what they have actually mentioned. So for concept as well as for numerical, Sinjan and Simbala is one of the best. Right? FM White is also one of the best. Then if you see the third book which I have mentioned, the IIT Kharagpur professor S.K. Saum and Suman Chakravarti, they are the champion of the fluid mechanics. That is the thermal part, and it is very important book for mechanical. It is like a bible, you can say, for fluid mechanics. If you are going for gate exam, you have to solve the solved example of this textbook, because every year whatever the question is coming, new questions, they are copy pasting from their own textbook, right? The fourth one is K Subramaniam. You can only follow this for problems. They have given 1,000 problem combining all the chapters. It is very good for only problem, but there are mistakes in this particular textbook also regarding the final answer, regarding some of the data. Then the fifth one is RK Bansal. Again, that is not a very good book, because some of the mistakes are there in the conceptual clarity also. In conceptual, there are certain mistakes, but for a basic numerical, you can follow this particular textbook. Now again, you will confuse the five textbook you have mentioned. Which book I need to follow? It's up to you. From the top three, one to three, you can follow any book, any one book. Don't try to follow all the three books. Otherwise, you will be completing only the fluid mechanics in the upcoming 6 months. Only one textbook. It's your choice. Sinjal Simbala, FM White, or SK Song. Either one of them you can follow for the fluid mechanics. Please note down. Whatever my content is there, my content is basically from SK Som and Sinjal and Simbala. Now, initial 10 to 15 minutes, maybe you feel bored, but it is one of the very important part regarding the preparation for the GATE exam. What I will do when we will start our session, the lecture number one, I will skip this particular portion and directly I will be starting with the concept. Now, can I move to the next one? All of you have noted down. SK Som and Chakravarti, because they are the IIT Kharagpur professors, you know, and for mechanical, most of the questions, even 99%, they are basically what, copying pasting from their own NPTEL lectures or this particular textbook. Not on the weightage part. No, for aero, no. Somewhere the professors, they are copying pasting. Aerodynamics faculty, they will be following its own textbook, you know, own content, and they will be giving the question. That question you can get from the NPTEL lectures. But again, my recommendation is don't go for NPTEL lecture at the first instant. When you have the doubt, then only you go for that. Even NPTEL assignment, I have just compiled in the format of what, PDF, and I have given in the Google Drive. No need to worry about that, along with the notes. Now coming to the weightage part for the fluid mechanics, you can see the weightage for aerospace is basically varies from 3 to 4 marks. But in GATE 2022, they have given for 7 marks. In that year, they have given 7 marks only for from the what, fluid mechanics. If you talk about the GATE 2024 aerospace, they have given for the 4 marks. For mechanical, it is varying from 6 to 9 marks, sometimes 10 marks. Now, what are all the sources of practicing the questions? So this is the last slide where we are discussing the preparation part. Then I will be starting the concept. Now, the sources for practicing the question, the first is IGC notes and the questions. IGC notes and the questions. whatever the notes is there. If you talk about the fluid mechanics, whatever the my class notes is will be there, and my questions, they will be on the first priority, because whatever I'm going to discuss, that will be the next year gate question automatically. That is being the trend from the past 5 years, right? Second is the gate previous year question of aerospace, XC, mechanical, civil. Whenever you are completing any chapter, let's say you are completing the fluid properties, you had to solve mechanical question, you had to solve the engineering science question, you have to solve the civil question, and you have to solve the aerospace questions. What actually they are doing, they are jumbling. Sometime the previous year question of XC they are putting in aerospace, mechanical question they are putting in aerospace question they are putting in mechanical. Like this they are doing the jumbling, right? The third one is NPTEL assignment questions. The fourth is a test series, which is one of the very important part. After completing your syllabus part, after practicing huge amount of questions, after having a huge theoretical understanding, after solving the NPTEL assignment questions, after solving each and every questions of previous year questions, if you are not able to solve test series new question, then what is the purpose of studying that much? Suppose whether you have studied any concept, let's say you have studied any properties, density, you have solved 1,000 numerical on density, but how can you come to know that what is your ability? That means if I give 1,000 number one problem, whether you are able to solve or not, how you will verify yourself? By writing the test series. If you are getting the marks, automatically you are on a what good path. That means your conceptual clarity is there for the particular topic. Not getting good marks, that doesn't mean that you are on the wrong path. It means that you are a slow learner. You have to practice a lot further, and you have to keep writing the test series multiple times, multiple subjects, till the gate examinations. I'm telling you one story of the one student. There are many students, but I'm just telling one student's references. Whenever he used to write the test series at the initial days, he used to get a very low marks, very poor marks, like a 7 marks, 5 marks, sometimes 2 marks, 10 marks in test series. But he never gave up on writing the test series. He continuously wrote the test series like anything. And in the month of January, he started improving little bit, not much. And his rank, he got the all India rank 5 in gate examinations. I'm talking about the aerospace. That means a student who you don't believe that he may achieve this much of rank because it is not having the good college. That means there is no backup of conceptual clarity. Second is he is not at all getting the good marks even after practicing a lot. But one thing was sure, that he was a very hard working, very hard working. He keep on writing the test series, and he become automatically robot, a smart robot for the gate subjects. That means you throw any question. There was a moment, when I throw any question, he used to give the answer like anything before 10 days or 20 days of the gate examinations. So it is not always true that NIT or IITN or IST people will get the good rank in gate examinations. That is a very misconceptions. If you are from a basically middle college or tier 2 college, still you may be able to achieve a very good rank in the gate examination. Try to throw this particular myth in the dustbin right away, right now. Now, in the gate examination, whenever we are starting our any batches, we are having two types of student. One who is a very good student, no doubt he is having already the conceptual understanding from the BTech onwards. He just joined for the having the refreshment of any topic, right? For those type of students, it is very easy to get the very good rank in gate exam with a little bit of efforts. But second type of student, those who are struggling in understanding the concept, definitely they need to work hard for the initial few days to cop up or to get the level of what the other students are having, the type 1 students. This is the one thing. Second thing, the type 1 student which I mentioned, that is those who are having already the backup understanding a huge understanding from the college level onwards, or those who are from the very good colleges, if they will be not practicing enough, they may get the poor rank in the gate exam. So gate examination will not be basically it is not basically observing that whether a student is from good college or low college or medium college. They will be testing the patience of each and every student. Now IGC test series you can join a very good level of question which is already we have combined or compiled in this particular test series. You can contact Dinesh sir for that. Now, what is XC? XC is a paper that is containing the engineering science. That means XCA, XCB, XCC, XCD. That is for the MTech admissions, or MS no admissions. Basically, in IITs or NITs. Basically, in the XC we have to select the two papers like a fluid mechanics, solid mechanics, material science. We have other subjects, but their questions level for the XC is very good regarding solid mechanics and fluid mechanics. So those questions also you can practice because some of the questions from the XC already they copy pasted in aerospace in the recent 3 years. The fifth sources is ESC previous year question. It is only for mechanical. Engineering services previous year question regarding strength of material and fluid mechanics, because in the gate examination MSQ is playing a huge amount of role. Multiple select questions. Multiple select question you will come to know when you come to know about this MSQ accurately, when you know theoretical understanding of any topic. And theoretical question you will find very good in what ESC previous year questions. The sixth one is very important is IGC assignment that will be given the moment I will be uploading the class notes. The sir will be uploading this IGC assignment and he will be giving you this IGC assignment, and it is very important for getting the good marks in gate exam. Are you getting my point? Whether it is clear the sources for practicing the questions. And my different one more thing, it is very important, at the age of 22 and 21, or 23, sometimes we may lack the confidence, self confidence. But on the first day itself, on your whatever the notebook is there, on the first page you have to write that I will be getting within 10 rank, and I will be getting this 60 or 70 marks in the gate examinations. You have to just believe on yourself. Whether you are getting your motivation or not on a daily basis. Suppose early morning you are waking up and you're not at all getting any kind of motivation. So, sir, I'm studying engineering mathematics. I'm not feeling well because I don't know anything. Don't get panic at all at any point of time. Remember always that there is a solution for everything. If you are not getting any topic in engineering mathematics, try to follow the textbook. What the textbook you read line by line, still you have the time. At the initial days, for the few initial days, you have to struggle a lot. If you initially struggle, definitely the last 2 to 3 months you will enjoy like anything. Initially, if you enjoy, at the end, what will happen? A lot of things will be basically getting collected. A lot of doubts will be getting collected, and you may be getting frustrated, and you will leave the preparations. That happened with the 60 to 70% of the students, those who are starting the preparation for this GATE exam. So it is very important, my dear friend, to have the self-confidence. You just have to remember that anything, if you want to learn, you can just get the command over any topic. Now we have in a digital era where you can find anything. If you just mention in the Google, you will find anything. But whether you are understanding that whatever the Google is answering to you, that is okay. If you write any question, he will be answering you. But there are two ways to take it. One is you understand each and everything what the Google is answering. Second thing, you just by heart it. Okay, that is the answer. That's it. In GATE exam, you have to make a habit that you understand each and everything by your own. Okay, okay, these are the things which are there, and I need to understand this particular whatever the answer is given by Google in this particular manner. When you make a habit, this habit will be reflected in your gate preparation also. Getting my point or not? Why I have given the answer for Google? Because most of you, 99% or 100% students are using the Google nowadays. Whether it is daily basis question, like in your home also, if you want to go for any spot or places, you will be searching on Google. He will be telling you the directions. You will be owning on Google Map. In a Google Map, you will be having a lot of directions to reach that destination from your home or particular house. But whichever way is a shorter one, how you will come to know when you understand the Google Map how to read properly. See, if you ask 10 student, all the 10 students will able to type it and they will get it. Okay, okay, this is the Google Map, it is showing. But out of 10, only 2 or 3 may be knowing how to reach that particular spot in a very shortest way. Until unless you actually know this particular place or you gone before. Are you understanding or not what I'm saying? Try to correlate on a daily basis. Then only we can come to this particular subject called fluid mechanics. Yes or no, guys? Because it happened in our daily life that sometimes we used to get the answer, but actually we are not in a position to digest it. We try to buy at it. Okay, okay, these are the solutions, these are the answers which is given by Google for our queries. That's it. We never do the microscopic analysis of that particular answer. Okay, okay, what actually they are answering. It is habit of few students, and those students are sparkle or maybe getting a very good rank in the GATE examinations. Those who are having the curiosity to know each and every detailing of minor topics, and that is what the 360-degree analysis we're going to do in our subject called fluid mechanics. Now let us start from the chapter number 1, that is the properties of the fluid. Please note down. So I will not compromise the first thing in conceptual learning. Second thing, numerical ability. That means we will be solving huge amount of problem, and along with that, you have to be patient with my content. Right? I'm not a person who just give you the formula and directly I will be solving the questions. It is not going to happen in my classes. If it is so, then every student will be start learning from the textbook, and they might be getting very good marks in the GATE examinations. But that is not happening. If it is an examination of formula based thing, then every student will be start this studying the textbook. They are opening the textbook, learning the formulas, and getting the marks in the GATE exam. But why it is very difficult to get the good marks in GATE exam? That is what we're gonna look into these particular in our future sections. Now, when you finish reading this chapter, that is the properties of the fluid, that is the chapter number 1, you should have first thing. You should have a first thing that is nothing but a working knowledge of the basic properties of the fluid. What are all the properties of the fluid, right? And you should be understanding the concept of quantum approximations. Second thing, my dear friend, you should have a working knowledge of viscosity and what are all the consequences of frictional effect it causes in a fluid flow. In this particular demo class, I'm going to focus my attention on a second objective. That means we should have a working knowledge of viscosity. What is the meaning of viscosity? What can be the consequences? What is the effect of viscosity in a fluid flow? That is what we have to discuss. Are you getting my point or not? Tell me, guys. Now, some of the students they might be curious. So, 30 minutes gone. You have not studied. You have not basically taught anything regarding the concept. Again, don't worry about the content. Do not worry at all anything about the content, especially about the my classes or about the IGCs. Because the past 30 minutes, whatever we have discussed, that is a worth thing to do that, especially for the GATE exam. Sometimes we are lacking, sir, what is a good source of practicing the questions? You know, so these are the things which are very, very important to know before starting any topic or any lectures. Now, my different, no down. Fluid mechanics. First of all, what is the meaning of mechanics? Mechanics is basically it is a study of effect of forces. It is a study of effect of forces. Now, my different, basically we have the three kinds of state of any body. The body may be under rest conditions, the body may be under motion condition, or body may be under deformations. The body may be under deformations. What is you gonna study in your engineering mechanics, that you are going to study whether the body is under rest condition or under motion conditions. These two things we are going to study in engineering mechanics. What we're gonna study in our strength of material, we're gonna study in our strength of material about the deformations. Now, what is the difference between deformation and the motion? Tell me, guys. Deformation, my different. You can see the two example I have given. One is the engineering mechanics example where the rod is being getting hinged about the point A, for example, about the point O. This rod is getting hinged about the point O. Now, when it is getting rotated by the angle theta, now when it is getting rotated by the angle theta, what is happening? The relative distance between A and B. Let's suppose in a body of a rod O C, I am having basically 2 points A and B. The distance between A and C, let's suppose it is having a certain distance. This particular distance will not be changing even after the motion. Even after doing the angular motion, this particular distance between A and B will not be changing. When the relative distance between the particles of a same body is not changing, those body will be called as non-deformable bodies or rigid bodies. Non-deformable bodies or rigid bodies. What is happening in the strength of material? If you take a same rod, but if you hinge, instead of hinging, you try to fix it in a wall. That means you just have a cantilever beam or cantilever rod. You just apply the load P. There will be certain amount of deformations. After deformation, by default, you can see that the distance between A and B is getting what changed. When the distance will change, that body will be called as deformable bodies. Deformable bodies. This type of deformable bodies we are studying in what? Strength of material. And the body which is under rest condition or motion condition without any deformations, those we are studying in the what? Engineering mechanics. So engineering mechanics can be said that it is a dealing with the non-deformable bodies. Strength of material which is dealing with the what? Deformable bodies. But what about the fluid mechanics? It is dealing with all kinds of state of a body, whether body is under rest conditions or motion condition or deformation. All the three kinds of state of a stress, all the kinds of three kinds of state of a body, we are studying in the what? Fluid mechanics. Fluid mechanics. It is a study of what is the meaning of mechanics? Mechanics means it is a study of effect of forces. But if I mention fluid mechanics, that means we are studying the effect of forces in a fluid element, right? So this slide is basically telling you the differences between the engineering mechanics, mechanics of solids, and mechanics of fluids. Now, in our next slide, we're gonna study the difference between the solid and fluids, solid and fluid medium, which is very very important to discuss that. You can also understand by giving one more example. Let's suppose you're not able to understand the rod, hinged or cantilever. You may have the body like this. In engineering mechanics, whenever we apply the force, let's suppose we are applying the force on the top of the box, it will be getting displaced to these positions, new positions, without having further deformations. Or maybe if I just apply the forces, something like this. That is what happening in the engineering mechanics. That means it is getting displaced from one location to another locations. The distance between the particle is not getting changed. But when you talk about the strength of material, if you take a same body, if you take a same body, my friend, and you just apply the force, there will be certain amount of deformations. There will be certain amount of deformations. That is what we're gonna study in our strength of material. Are you getting my point or not? All of you understanding? Can I move to the next one? Not all. The difference between the solid and fluids. The difference between the solid and fluids. Just note down the slide, then I will be starting my discussions. Now you can see the solid element and the fluid element I have considered as a water in our right side. Left side we have the solid element. Solid element which is rigidly connected with a movable plate, and on a movable plate I'm just applying the shear force. When I just apply the force, the solid body will be getting deformed because we are applying the shear force. Then whatever the deformation is there, that deformation d theta we are calling what? Shear deformations. Shear deformations. A solid block which is rested on a fixed plate, and on the top of that there is a movable plate. This movable plate, I'm doing, I'm just moving with the force called F. Because of the shear force which we are applying on a movable plate, and we are applying on an area, let's say area is what? A. Let's say the area is what? A. Surface area is A. So if I will be dividing the shear force with the area, I will be getting what? Shear stress. That shear stress will be what? Directly proportional to deformation, angular deformations. We also call shear stress directly proportional to shear stress. This particular law will be called as Hooke's law for the shear. Again, you will study in the solid mechanics, no need to worry. Sometimes we represent the shear strain by theta, sometimes we represent it by gamma. So d theta is equal to d gamma. D theta is nothing but the finite deformation of finite strain, shear strain. This is the first point, and this is the second point. Don't worry about the second point. As of now, you note down only first point. Now, when you apply the any kind of shear force to the solid block, you are observing only the fixed deformation, or it is having a certainly continuous deformations. No, the solid block and the movable plate both might be welded together. Getting my point or not? And if I move the block, there will be certainly some deformation in the solid bodies, because solid bodies are what? Generally elastic in nature. They are what? Elastics in nature. So there will be certain amount of elastic deformations. Understand, d theta or d gamma, it is having certainly a fixed deformation or a continuous deformations.
So
I will be
what is
keep on
D
asking.
gamma, sir?
D gamma is basically the shear strain. Actually, we write theta or gamma, but here I'm just representing a very small deformation. So I'm writing what d theta or d gamma. Getting my point or not? D theta you can just note down the finite deformation of finite shear strain. If I need to have more deformations, if I need to have the more deformations, do I need to apply the same shear force? I need to increase my shear force. Think about it and then tell me.
We have to increase shear force.
Yes. You can just mention in the chat section also. Understand what I'm saying? Whenever if you want to have the more angular deformations or shear deformations, why we are calling this deformation to be a shear deformation, not a normal deformations or longitudinal deformations? Because we are applying the shear force. The force is parallel to the surface area or normal to the surface area. See, again that is a basic understanding. If I just apply the force normal to the area, because of this the normal stress will be developed, force upon area. But if I apply the force parallel to it, I will be getting shear stress. I will be getting the shear stress and I will be getting the deformation. That is nothing but shear deformations. If I need to get the more deformations, more shear deformation, do I need to apply more shear force, same shear force, or less shear force? Just try to look at the formula of Hooke's law for the shear. Shear strain you want to have more, shear stress has to be more, shear force need to be more because area cannot increase. We are not doing any kind of chamatkar, where you can reduce the area. Area is fixed. The plate area is being fixed. You have to increase the shear force. You have to increase the shear force. Come to the water, come to the fluid. You just apply the same kind of shear force. You will find at time t equal to t1, you will be having certainly this much of deformations. At time t equal to t2, you will be having what? This much of deformations. At time t equal to t3, you will be having certainly this much of deformation for this edge. Similarly, this edge will also be getting continuously deforming, something like this with the time. So what you are observing in the fluid that there is the continuously deformations are happening for a fluid element. This continuous deformations is called as flow. Here, the shear deformation rate is important, not the shear deformations, because we are not having fixed deformation. With each and every time interval, the deformation is changing. So we are very bothering about the time interval dt, where the deformation is begun, or where what is the deformation in dt time interval. Rate is important rather than only shear deformations, right? So no doubt, the shear stress is directly proportional to deformation rate. We also call shear deformation rate or shear strain rate. There will be continuous deformation of the fluid. Yes, it won't stop. Can you stop the flow condition, flow of water, until unless you are actually not applying anything called shear force? There in the solid mechanics, we are governing this by the Hooke's law, where the shear stress is directly proportional to shear strain. But in the fluid mechanics, we have certainly one law, that is the Newton's law of viscosity, where the shear stress is directly proportional to d theta by dt or du by dy. Why we are writing du by dy? You will get to know very soon. Please note down. Even you apply a little bit amount of force, shear force, the fluid will be start deforming like anything, and the deformation will be called as a flow. Are you getting my point or not? All of you understanding? Hello, hello, hello. That means if you take a fluid element and you have the mobile plate, You just move the plate with the help of force. The fluid element which are at the rest condition, they will be also be start moving with the plate like anything. This type of flow is called as viscous driven flow. Viscous driven flow. Now, my defend, if I just remove the shear force, whether solid may be able to regain its original shape and size or not. If suppose the deformation is within the elastic limit, definitely if I remove the load, the solid body may be able to regain its shape and size. But if you just deform it beyond the elastic limit, that means you are in the plastic limit or plastic zone, then you may not be able to regain its original shape and size. But if you are talking about the elastic limit, yes, it may be possible. That's why I have mentioned in the point number 2 as the solid may regain the shape after removal of, say, the stress or shear force. But whereas, my dear friend, the fluid element, the moment you remove the shear force, the fluid deformation is a continuous. It cannot able to regain its original shape and size. Are you getting my point or not? Tell me this. Is it done? What is the NLV? NLV is nothing but Newton's law of viscosity. And that's how we define the fluid. Note down. The fluids are the substances that deforms continuously under the application of tangential or shear force, no matter how small is the value of applied tangential force. Even you just apply the little bit amount of shear force, the flow will be the deformation will be like anything and it will be continuously deforming. But in the solids, we don't find this particular nature that where we have the continuous deformation. It is having a fixed deformations. Then for all,
Sir,
yes.
for this definition of fluid, are we neglecting the part of viscous effects of fluid for this particular definition? Because if there are no viscous effects, the fluid will obviously flow till infinite time.
No, see, we are discussing about the real fluid, right?
Real-
There may be certain instances you are mentioning the viscosity is zero. That means ideal fluid you are talking about.
Yeah.
Are you gonna talk about the ideal fluids? See, for ideal fluid also we have the certain amount of flow, right? Ideal fluid can also flow, right?
Yes, sir.
For the flowing condition, it is Of course, viscous play a very important role, but the viscous or viscosity will play a very important role when it is contacting with the any solid surface, right? In the air, for example, in the atmosphere, suppose hypothetically you have the fluid which is not having any kind of viscosity, but still it might be flowing, right? Yes or no?
Yeah.
Not on the viscosity. Your doubt will be getting clear after this particular topic. Viscosity. We represent it by the basically we give this symbol as mu. Just note on the 5 lines, then we will be discussing. To understand this particular fundamental property of the fluid, I'm giving you an example, like example of engineering mechanics. Let's suppose there is a solid body. It is just placed on a surface, and we are applying the force F. I'm talking about solid body. Of course, the solid body will be having certainly some self weight, and this there will be certainly some normal force that must be acting. Engineering mechanics is going on, right? Then I think there will not be any confusion regarding this normal reaction and mg weight. Yes or no? Now understand. If this surface is a rough surface which is having a coefficient of friction mu dash, what will be happening, my friend? If I draw the free body diagram of this solid object, if I apply the force F, the solid surface or whatever the rough surface is there, which will try to offer some kind of resistive force or not, in the form of friction, in the opposite to the direction of a motion. And what is the maximum value of this static friction force? Mu dash time n, right? Yes or no, guys? If you solid object will try to move in the forward direction in the positive x directions, what is going to happen, my friend? What we are finding, the rough surface will offer some kind of friction force that will try to oppose the motion of a solid objects. Motion of a solid objects, where n is what? N is nothing but mg. N is nothing but mg. The same phenomena, my different, it is happening in the fluid mechanics also. The same phenomena is also happening in the fluid mechanics also. That means whenever the two fluid element, whenever the two fluid layer or one fluid layer and one solid surface, they are under the relative motions. One will try to offer some kind of resistive forces, or one will try to resist the motion of other layer. Why they will try to resist the motion of other layer, other fluid layer? Because of property called as viscosity. That means whatever the role which is being played by mu dash, the same role will be played by what? Viscosity in the fluid. Whatever the role which is being played by mu dash in the solid mechanics, the same role will be played by mu viscosity in the fluid mechanics. Now read the line. When the two solid bodies in contact move related to each other, a friction force will be developing at the contact surface in the direction opposite to the motions. As we know, we are applying the force F in the positive directions. Obviously, the motion will be there in the positive x directions. This situation is very, very similar when a fluid moves relative to solid, or when the two fluid moves related to each other. The property that represents the internal resistance of a fluid to the motion is called as viscosity. Put a note point and note down. Because of the viscosity, because of viscosity, the fluid will oppose or resist the flow between the fluid layers. Because of the viscosity, the fluid will oppose or resist the flow between the fluid layers. You take example of water and honey. If you try to flow the honey on a surface, and if you try to flow water on a surface, which will flow fast? Obviously water, right? In a particularly, if you talk about the viscosity of the honey, it is very high, so that it will try to offer resistance to each and every fluid layer, so that every fluid particle will be slowed down and they will be moving very slowly. Whereas in the water, that much of viscosity is not there, that much of resistance will not be there to the fluid motion, and they will be flowing freely as compared to honey. Now let us look at the concept of something called no slip conditions. No slip conditions. And why no slip condition is important? Boundary layer formations, all these things are the consequences of viscosity. All of you have noted down? Yes. See, fluid means fluid we can categorize into liquid as well as gases. Air is also one of the what? Ideal gas, right? Are you getting my point? Now you will come to know more about the viscosity. No need to worry. We will be studying in detail about this. But let us look at the consequences or impact, a bad effect. Let's say bad effect or positive effect. We don't know yet. But let us discuss the effect of viscosity. Then again, we will come back to this topic called again viscosity. Can all of you have noted down? Now, my dear friend, you just note down this particular concept called no slip conditions. No slip conditions. Whenever a fluid is flowing over any solid surface or body, the relative tangential velocity between the fluid and the solid surface will be equal to zero. Now let us look at this example where the fluid is flowing over the flat plate. This flat plate is being fixed one. That means you take a plate and you put it in the atmospheric air. Then what is going to happening? Microscopically, we're going to discuss this segment. Let's suppose before contacting the plate, each and every fluid particle is moving with a certain free stream velocity 10 meter per second, for example. Or better you just note down the diagram first, otherwise you will be keep on writing simultaneously, you will be understanding. So that is a confusion. First complete the diagram. Again, I'm saying you have to be patient in my class. Each and every doubt you have, whatever the doubt you may have, will be getting clear after each and every slide, one by one. At the same time, if you rush, sir, please clear my doubt straight away, right now, at this right moment. It is not possible for me because there are many pending topics that I need to cover to clarify your doubt fully. So you require a lot of patience in my classes. That is the one thing I'm guaranteeing you. And those who are understanding, those who might be thinking it's a solid and fluid is a very basic topic, sir. In GATE exam, whether they will be asking, already they asked the question. If I'm writing ABCD also in slide, that may be the next year GATE examination question. Never underestimate any content of my slide. Any corner thing which I'm mentioning in the slide, please make a note of it. Very, very important for GATE exam. If you just go back and check the history of previous year students and batches, I used to take the classes, and on my basically whatever the slides are there, they are basically whatever the questions they are getting from my slides only. Whatever the new question I'm talking about, not the old question, previous year based questions. We are here to discuss the new question which you are able to attend in the GATE examinations, right? Now drop your pen now. Just drop down your pen now and try to focus on the screen now. All of you have noted down? Tell me, guys. Whether all of you have noted down? Please note down. Then I will be starting our discussion on this topic. Otherwise, if I will be explaining, then you will be start writing. Then again, you will be asking, sir, what you said. Can you repeat it? I don't want that. Please complete it. Then close your notebook, keep it aside, and focus your attention on the screen now. Once you complete it. Because at least 20 questions you may be able to solve from this slide. You may not be able to believe, sir, how 20 questions you will come to know one by one. Is it done? No. Try to focus your attention on the screen. Just forget your all the past memories of this concept. Just focus freshly on this topic. Let's suppose the plate is being fixed, right? That is a flat plate. Again, 2D figure, you cannot visualize that there is a width also for this plate. This plate may look like this, which is having a certainly some width B and some length L, over which this flow is happening, my dear friend. But the width as of now, I can assume that 1 unit or maybe B unit perpendicular to this laptop screen. That you can understand. It's a 2D. I cannot draw the 3D figure. Okay. Second thing, my dear friend, the fluid is there with the how many layers I have shown? I have shown 7 layers. 1, 2, 3, 4, 5, 6, 7. The 7 layer, actually many layers are there, but to have understanding, I am just showing only the 7 layer of the fluid particles. Before contacting, they are having the what uniform velocity profile. Because each and every fluid particle, they will be moving with the same velocity, yes or no? Or do you believe in atmosphere, one air particle will move certainly 5 meter per second? In other fluid particle, they will be start moving in 10 meter per second at the same location. Suppose you are in the city of Bangalore right now, Whatever the air particle velocity will be there, it has to be same or different. Think about it and then tell me. I'm going with a very basic thing, guys. Very, very basic thing. How it is different, yeah. Suppose you are at the electronic city right now, in a Bangalore city, or maybe at the railway junction you are having right now. Near to the railway junction, how the atmosphere particle velocity can be different? It has to be same. And that is what I have taken the free stream velocity u infinity 10 meter per second. Just for the example, I'm saying. Just for the example, I'm saying 10 meter per second. It can be anything. It depends on the location to location. Now, before coming in contact, they are having the uniform velocity profile. Let us suppose this section is called as C section. Now you focus your attention on the A section. A section. After contacting, my friend, what is happening? After contacting, what is happening, my friend? There will be certainly some kind of velocity gradient will be exist. Certainly some kind of velocity gradient will be existing, my friend. Certainly some kind of velocity gradient will be existing, my friend, as you can see. Now focus your attention on the A segment. Focus your attention on A segment right now. The first fluid particles, the first fluid layer, before contacting, it is having a certain velocity u infinity. After contacting, the whatever the fixed the plate is there, which is having a velocity 0, the first fluid particle should have 0 velocity or non-zero velocity. To satisfy the no-slip condition, whenever a fluid particle is flowing over any solid surface, the relative tangential velocity between the fluid and the solid surface has to be 0. That means whatever the velocity of a fluid particle, velocity of a plate need to be 0. Velocity of the plate is 0. The velocity of the fluid particle, which is just attaching to the plate, it has to be 0 to satisfy the no-slip conditions. What about the second fluid particle? Second fluid particle will be having the same velocity before contacting and after contacting, or it will have certainly lower velocity as compared to the what? Previous segment. That means before contacting. Definitely, my friend. See, viscosity is the property. It is representing one kind of bonding between the fluid particles. Bonding between the fluid particles. Before contacting, they are having all are having the same velocities because they never get disturbed by any solid object. The moment if I place the solid object, they are getting disturbed. The first fluid particle, what the communication will be happening between the first fluid particle and the second fluid particle and the third fluid particle? The first fluid particle will say to the second fluid particle is that, hello, now I got stuck by the solid wall and I cannot move actually. My leg is getting stuck. I cannot move. Second fluid particle, what it will say? Okay, we have the huge bonding between them before contacting, and now also we have the bonding. But third fluid particle, what it will say to the second fluid particle? Hello, why you are not moving? Why you are not moving actually? Let me show you the third fluid particle here, second fluid particle here, and the first fluid particle here, which is being attached to the solid wall. Third fluid particle, it will try to move the particle 2, but the second fluid particle is getting retarded by the first fluid particle. In competition, third particle, it will try to move it. First particle, it will try to retard the motion of a second fluid layer. The resultant is that the second fluid particle is getting actually retarded. Not to the 0, but it is getting retarded by certain amount. Now, what the communication will happen with the third particle and the fourth particle? Fourth particle is saying that why you are not moving? I'm just moving with the handsome velocity. But third particle will say, no, I got stuck by the second fluid particle. Already communication happened that we have the huge bonding, but it is getting slowed down. So I also need to get slowed down. But the fourth particle will say that no. I have the bonding between you as well as having the bonding between the I'm having the bonding with the fifth particle also. Fifth particle is saying to me that you try to move it, but you are saying to me to get stop it here itself. So what the communication in the competition, what will be their scenario? The fourth particle will also be moving, not with that 10 meter per second, but certainly more less than what, 10 meter per second. Definitely more than third fluid layer after contacting. In doing so, in a y direction, we will be observing there has to be a velocity gradient exist. And this velocity gradient will be keep on happening up to certain distance from the solid wall where it is attaining the 99% of the free stream velocities. Where it is attaining 99% of the free stream velocity. The moment it is attaining the 99% free stream velocity, and if you draw the locus of all those locations, you will be finding one layer. That layer will be called as a boundary layer or hydrodynamic boundary layer. And whatever the thickness we are measuring in a normal direction, that means perpendicular to the wall, where the velocity is 99% of the free stream velocity, that distance will be called as boundary layer thickness, delta. So that is the first way of understanding. Now look at the second way of understanding. Suppose I'm taking the first class today. Let us suppose this is not a demo class, this is the first class, and this is my first class here. Or let us suppose, let's say we have the first, here we have the demo class. Whatever the section C is there, that is my demo class. Demo class, every student is attending with a lot of enthusiasm, lot of patience, lot of energies. The moment I am entering to my first class of the fluid mechanics, what will happen? Some of these students, those who are not at all motivated, they may be getting slowed down by some other means, by other subjects, and the same reflecting in my subject also, and they are basically retarded. That means they are having negative energy. That means they are saying that to the other student that what you will do by studying. There is no meaning of that. Anyway, the GATE examination is very tough. You cannot crack it. And this communication will be communicated to what other student like 2, 3, 4, 5 in the y directions. They will be anyway they are motivated, but their motivation will be what, getting down slowly. Definitely slowly their motivation will be getting slowed down. And who will be affecting a lot? The second particle or third particle, or maybe second student or third student. Who will be affected a lot in the first class? Suppose the particle 1 or student number 1 is basically a very negative person who is spreading the negativity about the class. Definitely second student who are very much close to the student number 1, he will be what, affected a lot. But what about the affection rate in a y directions among the students? That definitely will decrease because they are not that much, closely to the wall. Those who are very close to the wall, they will be affected a lot. What is happening in my second class? Let's suppose now I am in the second class, section B. In a second class, the first particle, whatever the first student is there, automatically he is totally negative person. But what the second student will be saying right now? In the first class, I also have some motivation, but in second class, you have demotivated me like anything. I'm not at all interested. Second particle will be getting slowed down. Definitely not zero, but it will be definitely having lesser velocity as compared to the section A. Definitely very less velocity as compared to the section C. So now the fluid particle need to travel larger distance, my friend, to achieve the 99% of the free stream velocity, because now the negativity is being spread like anything. Now who is spreading the negativity in the y directions? Who is communicating? What is the messenger from the wall that the first fluid particle is getting slowed down? You please, above fluid layer, please getting slowed down. You also have to get slowed down. Who is communicating this message? No. By which property? Negativity is one of the property, right, for the student, right? In the student, there are many property: positiveness, negativeness. Here also there has to be certainly some properties, right, among the student. That property will be called as viscosity. Viscosity. That means if we just try to see I will come back to this slide. I'm just, for a second, I'm just moving to the next slide. The first layer, second layer, third layer. The third particle is moving with a certainly more velocity, u double dash. What the force of resistance offered by the second fluid particle onto the third particle? Towards the left, right? In Newton's third law, what the third particle will do to what the third particle will offer onto the second particle? In these directions. And that will become a driving force for the second particle. When the second particle will be started moving with the velocity u dash, the first particle who is just retarded, he is just very cruel, and he will be applying a huge amount of shear force, something like this. And by the Newton's third law, second particle will also apply some kind of reaction force on the what first particles. So you can see that what is the scenario over here? What is the scenario over here, my dear friend? The second particle is in what dilemma or not? Fs3 will try to move, Fs2 will try to resist. In a competition, the velocity will be getting reduced or not for the second fluid layer as compared to the C section. If I talk about the A section, for example, the fluid part velocity for each and every layer will be getting slowed down or what? Because of this viscous force. And what is the viscous force, my dear friend? You will come to know very soon. The viscous force is what? Tau s into area. What is the tau s? Mu into du by dy into area. That means shear force is what? Directly proportional to viscosity. If more and more viscosity is there, more and more resistive forces will be there. And more effect of slowing down will be there. Are you getting my point or not? So who is communicating the message? There is a bonding. Viscosity is what? One of the property. It is there because of what? Intermolecular force of attractions between the two fluid particles. Because of the viscosity. Why there is a viscosity between the fluid particles? Because of the bondings. And because of the bonding only, this message is getting propagated or not? How they are communicating? How they are communicating? Because of the property or not? Because of the bonding or not? And who is creating the bonding? Why the bonding is created? Because of the viscosity. Are you getting or not? Tell me, guys. So as compared
Sir,
to the section A,
why is boundary layer thickness increasing in next directions?
no, that is what I'm saying. That is what the next. I was actually talking about that only. If you compare the section A and section B, the boundary layer thickness is growing. Why the boundary layer thickness is growing? Because effect of slowing down is much more pronounced now. That means whatever the negativity is there, that negativity is getting spread like anything among these students, each and every after the class. So now to attain the same 99% of the free stream velocity, the fluid particle need to travel more distance or what? See, the third particle, it is getting slowed down. Earlier it is having certainly 4 meter per second, and now it is 3 meter per second. So slowly it is getting what? Gaining its velocity in the y directions. So definitely to achieve 99% of the free stream velocity, it has to travel more distance or less distance. Even if you compare this D section, further it has to travel more distance. Yes or no? Tell me, guys. Are you getting or not? So delta will be directly proportional to what? Under root of x for the laminar flow. If you will take x is infinity, delta will also be infinity. But that is not possible, you know. You cannot have the infinite length plate. Definitely you will be having finite length plate in your particular practical scenario. So you can note down the two definitions. One definition is regarding the boundary layer. Second definition is basically the boundary layer thickness. Boundary layer thickness. So what is the boundary layer? It is a very narrow region which forms when the fluid flows over any solid surface, and in this narrow region the velocity gradient will be existing. Are you finding the velocity gradient or not? If you see very carefully, you can see there is a velocity gradient which is measured with respect to vertical directions, theta. There is a difference of velocity. When there is a difference of velocity, my friend, definitely you will observe theta. You can write this as section C. Now, if you take example, certainly I am taking example number one, but if you take example number two, and if you take example of ideal fluid is it is not having any kind of viscosity. If it is not having any kind of viscosity, the whatever the particles are there before contacting, let's say they are having uniform velocity profile or uniform velocity u infinity. Even after contacting my friend, whether they will follow any kind of no slip conditions, any kind of communication will be happening, any kind of bonding will be existing between the fluid particles? No. Even after contacting the plate, they will be moving with the same velocity, uniform velocity. They will feel like there is no plate at all. So no slip condition is what? The no slip condition is getting violated. In that case, my friend, if there is a no communication is happening, if there is a no velocity gradient is existing, whether any kind of boundary layer formation will be existing for ideal fluid? See, the moment solid particles are there, suppose there is a solid surface. The first fluid layer it is coming in contacting with the what? The first fluid layer which is coming in contacting with the what? Fixed plate. Now this first layer and this particular fixed plate, there has to be certainly some communication will be happening. And because of the viscosity, there will be certainly some resistive forces will be developed on a first fluid layer. But as of now, we don't have any kind of viscosity. The resistive forces will be zero. If the resistive forces will be zero, nobody can stop the motion of a fluid particles. Definitely, if nobody can stop, how we can reduce the velocity? They will not be getting reduced, and they will be moving with the same velocity u infinity. And if they are moving with the same u infinity, the no slip condition is getting violated. Now they are getting slip. Now they are getting slip. And there's a further second, third, fourth particle, they will also be moving with the same velocity because there is no communication, whether they're getting slowed down or not getting slowed down. No communications, nothing. So there will not be any kind of boundary layer formations. Please note that. Of course, you have to remember this is valid only for laminar flow. For turbulent flow, we have some other. Of course, there also we have the delta is directly proportional to x, but not x to the power 1 upon 2. It is x to the power 4 by 5. We will discuss in boundary layer theory in detail. Is it done for all? So now you get to know as of now that because of the property of messenger, the first particle is messaging to the second particle, hello, please slow down. Second particle is saying to the third particle, please slow down. That's how the velocity gradient is existing, and there will be certainly some narrow region forms near the solid wall where this velocity gradient will exist. That narrow region will be called as boundary layer. So note down here two definitions, which is very very important. Boundary layer. The narrow region forms when the fluid flows when the fluid flows over any solid surface. And in this narrow region, and in this narrow region the velocity gradient will exist. The velocity gradient will exist. Velocity gradient means du by dy. Velocity gradient in the y direction, how the velocity is changing in the y directions will exist. This narrow region is called as boundary layer. This narrow region is called as a boundary layer. There is a fixed plate and there is a some uniform velocity profile is there. The fluid is flowing over this flat plate with the free stream velocity u infinity. We know that there is some boundary layer formation will be taking place. Now I am at this location right now. Where this fluid particle is attaining 99% of free stream velocity. The distance traveled perpendicular to the wall till the point the velocity is almost equal to 99% of free stream velocity or almost equal to u infinity. That distance will be called as delta. That means after this might event, we will be having uniform velocity profile like this. So note down the definition, boundary layer thickness. So now if I will be asking you, what is the region of boundary layer formations? What you will say? What is one of the major region for the formation of a boundary layer? Think and tell. Viscosity, yes. So that is the consequences of viscosity. The distance measure perpendicular or normal from wall till the point velocity is almost equal to the velocity is almost 99% of free stream velocity or velocity is almost equal to u infinity. This is the x equal to 0. This is the x equal to L, for example. This may be certainly some x is equal to capital X, whatever the location we have taken. Let us talk about the say deformation rate or velocity gradient. That means because viscosity is responsible for boundary layer formations. If there is no viscosity, no communications, no messenger will be there. It is acting like a messenger. You will come to know very no in our boundary layer theory you will get to know because of the viscosity the drag force is existing. Drag force is basically one kind of loss only. All these are the consequences of viscosity. Is it done for all? Again, coordinate system, you can mention the coordinate x in this direction, y in this direction. Note down, say a deformation rate. Just take a two plates, one plate is fixed and another plate is moving, and the fluid is under rest conditions. Then how the fluid is moving? The moment we apply the force F to move this movable plate with a constant velocity V, capital V, the fluid will also be start moving. The fluid will also be start moving. Let us suppose the velocity profile that we are getting in between the two plates is certainly some parabolic velocity profile. It can be linear velocity profile also, but we can have any kind of velocity profile. Let us suppose I am taking the parabolic velocity profile. As you can see, the parabolic velocity profile, and I am taking the two fluid layer which are there at a distance of which are basically marked as fluid layer 1 and fluid layer 2. The gap between the fluid layer is dy. Obviously, when the first fluid layer is moving with the velocity u, the second fluid layer is certainly moving with the higher velocity because it is very close to the movable plate. And let's suppose it is moving with the velocity called u plus du. In a dt time interval, let us suppose I am considering these two fluid particles, particle number 1 and particle number 2 of a fluid layer 1 and 2. In a dt time interval, let's suppose the particle number 1 is traveling a distance of what? Udt. Because you know that what is the velocity? Displacement by time. Then how much of fluid particle is getting displaced? By the amount udt. What about the second fluid layer? Second layer is having a velocity u plus du. If you multiply with the dt, how much of total distance is covered by the second fluid layer? Udt plus du dt. So if you join these particles, certainly you will be having what? Let's suppose you have the fluid layer AB 1, 2. After traveling, this is attaining a position of this much, and this is attaining a position of what? This much. So now, if hypothetically, when you believe that, just can you believe that there is a certainly some difference of velocity between the particle 2 and particle number 1? This is the total distance u plus du dt. Already u dt is this much. So what is the extra distance? Du dt. If you form a triangle in this one, what you are finding d theta? If you write tan d theta from here, if you write tan d theta, du dt, that is nothing but opposite side by base. What is the base? Base is nothing but dy. That is the gap between the two layers. We know that whatever the d theta is there, that is a very small. If d theta is very small, tan d theta will also can be written as what? D theta only. So what is the d theta? Du dt by dy. Now what is the d theta by dt? That is equal to du by dy. So what is the d theta by dt? Earlier we called, actually what is the d theta? Say deformation. But if I write d theta by dt, can we write say deformation rate or rate of angular deformations? And now you can see very clearly the rate of angular deformation is directly proportional. It is directly equal to what? Velocity gradient in the y directions. Are you getting my point or not? If we take a two fluid particles, two fluid layer, certainly at a distance y from the fixed wall, which is having a certainly gap of dy, then definitely there has to be certainly some relative velocities. Because of that, some distance will be extra distance will be covered by the second layer as compared to the first layer. That extra distance will be called as du dt, and if I divide by dy, I will be getting what? Tan d theta. That means that much of angle it is getting tilted. With that much of angle, it is getting deformed. With that much of angle, it is getting what? Angularly deformed. Are you getting my point or not? Tell me, guys. Yes or no? Whatever the fluid particles are there, my dear friend, let's suppose you have the two particles, fluid particles A and B. Let's suppose the moment the fluid is moving and there is a certainly more velocity, let's suppose it is having more velocity, definitely it will travel certainly more distance and it will be deforming this much only. The deformation in this fluid element for the first layer will be this much only. For the second layer, this much of deformation will be there. What is the extra deformation is there? By which this fluid layer AB is getting deformed by A dash, B dash, B double dash. This angular deformation is called as d theta. D theta. And d theta by dt is what? Du by dy. That means how much of velocity is getting changed by changing the y distance. By changing the y distance. And what is the Sayre strain rate? Already we know that d gamma by dt, that is equal to d theta by dt, that is equal to dy by du by dy. Please make a note of it. If the both the fluid particles are having the same velocity, tell me will there will be any kind of deformation, angular deformations? Do you believe that? Whether there will be any kind of deformations? Suppose the both the fluid particles are having u velocity and u velocity. You imagine the situation in a dt time interval, how they will be traveling. Suppose A particle and B particle, it is also moving with the u, it is also moving with the u. In a dt time interval, how much of displacement it is gone, how much of this deformation it is gone, this much of deformation. This is also this much of deformations. Now tell me whether any kind of angular deformation for this line in AB, whether line AB will be getting distorted. If there is a certainly some velocity differences, then only we are getting this velocity gradient, right? And why this velocity gradient is existing? Because of the property called viscosity. All of you have noted down this slide so that we can discuss the next concept, which is nothing but Newton's law of viscosity. Newton's law of viscosity. Is it done for all? All of you have noted down? No, guys, here. Complete this slide, very, very important. What you can start noting down from here. You know, you just start from here. Don't write this one. As of now, don't write this one. You start writing from here. Whatever the marking I have done with the red color. Newton's law of viscosity. According to this, the shear stress at a distance y from a fixed wall, at a distance y from a fixed wall, is directly proportional to rate of angular deformations. The shear stress will be directly proportional to du by dy, directly proportional to d theta by dt, directly proportional to d gamma by dt, because we know that d theta by dt is equal to du by dy is equal to d gamma by dt. Already we have proved it. If I remove the proportionality constant, I will be getting what? If I just remove the proportionality, I will be getting proportionality constant. That is nothing but This proportionality constant will be called as coefficient of viscosity or dynamic viscosity mu. That means tau can be written as equal to what? Mu times of du by dy, mu times of d theta by dt, mu times of d gamma by dt. Then after this, you note down this last one. The fluids for which the rate of angular deformation is proportional to the shear stress are called as Newtonian fluid. That means the fluids which follows Newton's law of viscosity is called as Newtonian fluids. That means the fluid which does not follow the Newton's law of viscosity will be called as non-Newtonian fluids. Is it done? Please note down. Is it done? Note on the few points. If I take the fluid layer, for example, at a distance y, you can see that suppose the fluid is flowing, and I'm just taking the fluid layer at a distance y from a fixed wall, and just I'm applying this shear stress tau, and I need to find the shear stress. What I will be doing? I will be multiplying mu with the du by dy. That's it. But remember, whenever we are finding the tau at certain location, let's suppose I am finding the y. See, this is the y. The small y is basically the distance from the fixed wall. And now I'm calculating the tau at a distance y is equal to h. So what I need to do? I need to put y is equal to h or what? Because du by dy is continuously changing or constant for a parabolic velocity profile. Suppose you have the velocity profile, something like this. Don't you believe that the gradient is changing continuously? Tell me guys, what do you believe? Whether the velocity gradient is continuously changing in the y directions. Here it is maximum, theta 1. Here what is the value? theta 2. Here, what is the value at the 99% of the free stream velocity? Theta 3, which is 0. So it is continuously changing. So definitely, whenever we are finding the tau, we need to keep the values of y at that location. Again, note down the one more definition. Again, it's the same definition only. Whatever the definition for the Newton's law of viscosity, the same definition goes for the Newtonian fluid also. The fluid which follows the Newton's law of viscosity will be called as Newtonian fluid. In our previous slide, what we have written, the fluid for which the rate of angular deformation is directly proportional to shear stress. This line is also what? Newton's law of viscosity, right? So directly what we can say, the fluid which follows the Newton's law of viscosity will be called as Newtonian fluid. What is the example? Air, water, mercury, petrol, diesel, etc. If I plot, just say tau is directly proportional to du by dy, that means y we can say directly proportional to x. Y is we can say mx. That means one of the straight line I will be getting if I plot tau versus du by dy. Then whatever the slope of y axis and x axis is there, that I'm calling m, this slope will be what? If I take the slope of tau versus du by dy, I will be getting the slope as mu only, because if we compare this equation with the what? Mu times of du by dy. If you compare these two equations, you will be getting m as what? M as mu only. So whatever the slope of shear stress and the velocity gradient, that will be called as viscosity. This is what the slope I am taking. No, non-Newtonian fluid, we have a lot of examples, like you can say blood. No, blood. What is the other example? Toothpaste. Yes or no, guys? What are all the other examples we have for the non-Newtonian fluids? Ice cream, you know, gypsum paste. Whatever the paints are there, some of the paints, you know, sugar in water solutions. These are the example of non-Newtonian fluids. And what we are finding, this slope is constant for a straight line or what? Whatever the straight line, whenever we are drawing, what is the slope of this straight line? Will always be constant with respect to x, or it is varying with respect to x. If you have y is directly proportional to x, then whatever the slope is there, this slope is constant every location or what? It's constant. That means the slope is what? Is constant. If you plot m versus x, it is constant. Now here, what is the slope? Viscosity. So if you plot viscosity versus velocity gradient, you will be getting you will be getting what? One constant line. But this line will not be constant in case of non-Newtonian fluids. The viscosity will be keep on changing. So whatever the slope of tau versus du by dy will tell you the values of viscosity. That means if this slope is more, then the viscosity will be more. If slope will be less, viscosity will be less. See, on a y-axis we are measuring the slope with the horizontal, but in our fluid mechanics, whatever the rate of deformation we are measuring, whatever the velocity gradient we are measuring with respect to y-axis. Are you getting my point or not? Do not get confused. Let me write theta dash. Yes or no, guys? Whatever the slope of whatever the velocity gradient we are measuring, for the velocity profile, we are measuring with respect to y-axis. But in the universe, apart from it, whatever the slope we are measuring, we always measure with respect to horizontal. Yes or no? In your mathematics also. Tell me, guys. I'm just trying my level best to connect the dot between the other subjects. Yes or no? Please note down this graph, the shear stress versus rate of deformation du by dy. I'm just drawing the plot for air, water, and oil. All of you know that oil is having more viscosity than water than air. So obviously, if I want to plot air, water, and oil on a shear stress versus velocity gradient, definitely you will be finding the slope has to be more for oil than water than air, because viscosity for the oil is more than the water than the air. You can see that air is having very less slope. That means it is having very less viscosity. Now we will try to look into the SI unit of viscosity. Is it done? Done for all? Now for the time being, my friend, I'm assuming the velocity profile between the two plates is a linear velocity profile. Just for the sake of understanding and easiness, I'm assuming the velocity profile to be as a linear velocity profile. If I assume the linear velocity profile, whether my slope will be getting changed or not changed in the y directions. If I assume the velocity profile to be a linear one, whether my slope will be getting changed, it will not change. Then what is the theta? What is the theta dot? For example, u by L. So what is the du by dy? That can be written as y2. Let's suppose this is a particle number 1, particle number 2. u2 minus u1 divided by y2 minus y1. So that will become what? u1 is 0, y1 is 0, y2 is what? L, where y is the distance from the fixed wall. So you will be getting what? U by L. The same thing I have written, my defect. Actually, it is V by L because the plate is having certainly some velocity. This velocity is what? Capital V. So please note down. We know that the Newton's law of viscosity, the tau is directly proportional to du by dy. If I remove the proportionality, I will be getting proportionality constant. Tau is equal to mu times of du by dy. Du by dy for the linear velocity profile, we know that it's a V by L. So tau is what? Mu times of V by L. Tau, we know that force by area. Then what is the viscosity? F by A into L by V. F by A into L by V. F by A into L by V. Now what is the force? Newton. What is the area? Meter square. What is the length? Meter. What is the velocity? Meter per second. If you try to simplify, you want to get Newton second per meter square. Newton per meter square, already we know that it's a Pascal. It's a Pascal. So we can also write SI unit of viscosity as Pascal second. Pascal second. You can also have the SI unit something like this. What is the force? mg, ma, mass into acceleration, kilogram meter per second square, area meter square, length meter, velocity meter per second. Automatically it will be second. So further, if you simplify, I will be getting what? Kilogram per meter second. That is also one of the SI unit. So we have the two SI unit. One is a Pascal second. Second is what? Kilogram per meter second. If you talk about the CGS unit, if you talk about the CGS unit of viscosity, we can write it as 1 gram per centimeter per second. 1 gram per centimeter per second. This is called as 1 poise. 1 poise is nothing but 1 gram per second per centimeter. If you try to convert in kilogram meter second, you gonna get like 0.1 Pascal second. That means one poise is what? 0.1 Pascal second. And if we note down the dimensional formula, already we know that what we know, my different. We know that Newton second per meter. What are the Newton unit dimensions? M into A, mlt minus 2. What is the dimension of second t? What are the dimension of m? L square. If you simplify, you're going to get ml minus 1, t minus 1. That is the dimensional formula for viscosity. Remember, viscosity is having three names: dynamic viscosity, coefficient of viscosity. There is a one more term called kinematic viscosity that we will be discussing when we start our session. Are you getting my point or not? Is that clear? Done for all, so that we can discuss at least one or two numerical. Now we will try to look at some of the questions. Now you can see the question number 1. Consider a velocity distribution of u as a function of y. Now for the two adjacent fluid layer L1 and L2, the viscous force exerted by L1 onto the L2 will be what? By looking at this scenario, there may be the lower plate which tries to move like this with the velocity v, and basically the upper plate is fixed one, and basically we have the two fluid layer which are there at a distance. Let's suppose this is the fluid layer L1 and this is the fluid layer L2. What they are mentioning, they are asking what is the viscous force exerted by the L1 onto the L2. Definitely, whatever the velocity for the second fluid layer, it has to be more u plus du as compared to the L1 fluid layer, because layer 2 is near to the bottom plate. So whatever the force exerted, my different, whatever the force exerted by this what we call L1 fluid layer, it should be acting what? It should be acting what? What is the viscous force? Viscous force will try to reduce the velocity of the adjacent fluid layer. How it can reduce the velocity of a second fluid particle? By applying the resistive force in this leftward directions, so that it can reduce the velocity of the second fluid layer. By the Newton's third law, second fluid layer will offer some kind of resistive forces in onto the what? Layer number 1 in the forward directions. So what they are asking, the viscous force exerted by L1 onto the L2 towards the left. But if I will be asking you what is the viscous force exerted by L2 onto the L1, it should be towards the right. Getting my point? Yes or no, guys? Are you getting my point? Yes or no, guys? Now we will try to understand one numerical. I hope you have noted down. Can I move to the next segment? The last question for today's session. Done. Yes. Please make a note of it. This is the question 2 which we are discussing. Consider an incompressible 2D cuvette flow. Cuvette flow, I already mentioned, it is a one kind of flow which is happening between the two plates, in which one plate is fixed one and the other plate is moving. The lower plate is the lower wall is kept stationary. What is the shear stress acting on a lower wall if the upper wall is moving at a constant speed of 2 meters per second? The viscosity of the water is given in the problem, Newton second per meter square. Now in this question, whether they have given any kind of velocity profile, whether we have to consider like a linear velocity profile or parabolic velocity profile, something like that. By default, they have not given anything regarding the velocity profile, but they have given the incompressible flow and cuvette flow. For incompressible, my default, which is having a dp by dx pressure gradient 0, for this condition we can assume the velocity profile, not assume, we are going to get the velocity profile as linear velocity profile. Again, I'm not discussing how we are getting the velocity profile as a linear velocity profile. The moment we will be starting our course from the lecture number 1, most probably in the lecture number 2, again I'm going to solve this numerical, and again there I will be telling how we are getting the velocity profile as a linear velocity profile from the Navier-Stokes equation in the x directions. This type of flow where the pressure gradient is 0 in x direction, this type of flow is called as viscous driven flow. Viscous driven flow. How we are seeing the viscous driven flow? See, because the plate is moving, so whatever the fluid particle which is near to this one, they will also be moving. Why they are moving? Because you know that this fluid layer will try to oppose this motion of the plate. They will be applying the forces like this, and by Newton's third law, it will apply the force like this, and this force will become what? This F2 force will become what? Driving force for the fluid particle, and that drives the fluid. Whatever the fluid which are at the rest condition, they will be start moving. So now we are assuming the velocity profile for the time being. The velocity profile is a what? A linear velocity profile. For a linear velocity profile, my defend, what is the shear stress? V times of du by dy. Let's suppose the v is given as 2 meter per second. So this can be written as v by h. What is the h? H is nothing but 1 meter. So what is the shear stress? 7 into 10 power minus 3, 2 by 1. So what we can write? 14 into 10 power minus 3 Newton per meter square. D has to be correct. But this is the shear stress we are getting on a lower wall. If I will be asking you what is the shear stress on an upper wall, what will be the answer? By looking at the shear stress, whether it is depending on a y coordinate or not. If you look at the expression of a shear stress, it is depending on what? Mu, v, h. All these three terms are constant or not constant. All these three terms are constant or not constant for a given flow conditions. All these three parameters are constant or not constant for a given flow condition. It's a constant. So can I say the shear stress has to be a constant? That means my defend whatever the shear stress, whether they are asking on a lower wall, intermediate fluid layer, or upper wall, the answer must be 14 into 10 power minus 3 Newton per. Please make a note of it. Once it is done, we can leave for the day. Thank you all. All of your understanding or not? Again, I'm saying how we are getting the linear velocity profile. I will be deriving from Newton's, Navier-Stokes equation in x directions. Once I will write the Navier-Stokes equation in x directions, then I will be saying how we are getting the velocity profile as a linear velocity profile. Don't assume directly. Once it is done, let me know. So whether this particular class is useful or not. You may not be getting 100 out of 100 thing, but something you might be getting, right? Okay. Thank you all. Yes, yes, I will be sharing. I will be sharing.